Hi everybody, I hope this video finds you well. In today's video, we're going to be starting into section 11.10 from your textbook, which is sort of the culmination of all the stuff that we've been discussing about power series representations of functions. To do this, we're going to learn how to build what are called Taylor or Maclaurin series for different types of functions. So to do this, what we're going to do to start off with is sort of consider the idea of building a power series representation from a different perspective. In the past, what we sort of did is we based all of our sort of results around the idea of taking that one series that we knew how to sum up, the geometric series, and manipulating it as much as possible to build power series representations for the logarithmic function and as well as for the inverse trigonometric function, the arctan of x function. What we want to do in this sort of section, though, is consider this problem from a different perspective. So far, we've been taking a sort of series that we knew stuff about and trying to manipulate it as much as possible. Now we're going to take a much more sort of general approach, and we're going to sort of imagine that we have a function and we're going to just assume that it has a power series representation. So we're just going to start off by assuming that there is some power series, some infinite polynomial that represents our function f of x. And what we're going to do is we're going to sort of work backwards from this to figure out what can we really say about those a sub n values. So, in other words, what we're going to do is we're going to suppose that we have some function f of x, and we're going to assume that it has a power series representation centered at x equals c. Now, it's a big assumption that it has a power series representation, and we'll see in the sort of second half of 11.10 what allows us to make that assumption, but for now, we're just going to assume that it does have a power series representation. So in other words, we're saying that we can say f of x is equal to the sum from n equals 0 to infinity, a sub n x minus c to the n. And our goal is to say, based on this equality, what can we say about those a sub n's? So in other words, can we try to determine maybe some expression or a way of figuring out what those a sub n's should be to make this equality work? So let's sort of explore this just from the idea of trying to directly manipulate this as much as possible. So we have this f of x is equal to this sum n equals 0 to infinity a sub n x minus c to the n. Maybe to help ourselves, let's begin by just writing out the first few terms here. So if n equals 0, then this x minus c to the 0, of course, is just 1, so we would just get a sub 0. Then plus at n equals 1, we would get a sub 1 x minus c. Then at n equals 2, we get a sub 2 x minus c squared plus a sub 3 x minus c cubed plus a sub 4 x minus c to the fourth plus dot dot dot. Okay, that should be enough terms, right? That's what this power series representation centered at x equals c should look like. All right, now remember, our goal is to try to learn something about each of these members of the sequence, each of these values of the sequence, a sub 0, a sub 1, a sub 2, a sub 3, a sub 4, so on. Okay, so the first thing we should notice is that we could maybe learn a little bit about this a sub 0 if we could get rid of all these. Notice that all of these, though, have x minus c in them. So let's go ahead and do an evaluation. Remember, this is a functional equivalence. This function is equal to this infinite polynomial function. So it has to be true at any particular x value we pick. So let's go ahead and let x equal c, whatever the center value is. Now, if we do x equals c, all of these things will zero out. So notice on the left-hand side, we'll get f at c, the function evaluated at the center, has to equal a sub 0. And let's go ahead and just box that for right now, because this, notice, if we read it this way, tells us that a sub 0 is equal to f of c. So we know that our first value in the sequence, a sub 0, should be our function evaluated at the center. Okay, unfortunately, that's all we can really get from here, because if we think about it, if we try to plug in anything else, well, we know what a sub 0 is, but if we plug in any other value, all of these terms will still remain, and while we might know this one, we'll have an infinite amount of other things that we need to determine. There's no way we're going to be able to do that. So let's instead make use of something we discussed in the previous video, which is that we can differentiate this. So let's differentiate this thing now. Notice that if we do that, we'd get that f prime of x, which is the derivative on the left-hand side. If we differentiate on the right-hand side, this will drop out, and we'll get the derivative of this, the derivative of x minus c is just going to be 1. So we're going to get a sub 1 plus, here we're going to use power rule. We're going to have to drop the 2 down, 2a sub 2 x minus c. And of course, the derivative inside here is 1. So even though there's chain rule, it's not changing anything. And then plus 3a sub 3 x minus c squared plus 4a sub 4 x minus c cubed. Okay, and then of course plus dot dot dot. There's a ton more things that we're differentiating. There's an infinite amount of things over here, but we're just looking at the first few. Now notice the advantage of that. Now all of these things have that x minus c, but this does not. So again, let's go ahead and let x equal c. Well, all of these pieces are going to zero out, and we're going to get that f prime at c has to be a sub 1. In other words, a sub 1 needs to be f prime of c. So now we've determined the next value in our sequence. A sub 1 needs to be the derivative of our function evaluated at the center. Okay? We might be already sort of seeing a pattern here, but we need to go a little further to establish that pattern. So let's go ahead and take a second derivative. So f double prime. Differentiating over here, this is going to drop out. Here, when we differentiate that, we're just going to get 1. So it's going to be 2a2 plus. Differentiating here, we drop that 2 down. Now, 3 times 2, we all know that that's 6. But for now, I'm just going to write that as 3 times 2 times a3 x minus c. I'm not going to simplify anything. And then plus 4 times 3 times a sub 4 x minus c squared. And then plus dot dot dot. Once again, notice that everything this way is always going to have that x minus c term. So if we let x equal c, well, then we get f double prime at c is equal to, all these things will zero out, and we'll get 2a2. Now remember, we're trying to solve for these values in the sequence. So we need to isolate this. Let's divide that 2 onto the other side and get f double prime at c divided by 2 is a sub 2. Okay, now this tells us that the pattern maybe that we were seeing isn't quite as simple. Back here, it might have been thinking that, oh, the function is a sub 0, the function at the center, the first derivative is the first one. Maybe this one was going to be the second derivative is the second one. Well, unfortunately, it's the second derivative divided by 2, though. So it's the second derivative evaluated at the center divided by 2 gives us our a sub 2. Okay, let's, just because we have to move on to another page, let's remember that we have this so far. And we're going to need to differentiate one more time at least to sort of see this pattern. So let's give ourselves one more sort of page here. There we go. So far we have this right here. Let's go ahead and differentiate again. So we can have f triple prime. Of course, when we differentiate that, that's a constant, so that'll drop out. Here, looks like we'll have 3 times 2 times a sub 3 plus 4 times 3 times, and then this 2's got to drop down there, so times 2 times a sub 4 times x minus c plus dot dot dot. Okay, same trick. Let's go ahead and let x equal c. On this side, we'll get f triple prime evaluated at the center. Here, we'll get 3 times 2 times a sub 3. And then all this stuff down here, all is going to zero out. So notice if we're solving for a sub 3, we would get that f triple prime at c is divided by 3 times 2 equals a sub 3. So at this point, we should be pretty convinced that the index of our sequence directly corresponds to the derivative that we need. Right? If we look back here, we had that this first one, a sub 0, was with the 0th derivative, the original function. A sub 1 was based on the first derivative. A sub 2 was based on the second derivative. And a sub 3 is based on the third derivative. But what's going on in this denominator? Well, here you could sort of think about the denominator as 1. Here the denominator is 1. Here the denominator was 2. And then here it's 3 times 2. And if you look ahead, the next one's going to have a denominator of 4 times 3 times 2. What is that sort of resembling? Well, that denominator down there isn't just based on the index, it's actually based on the factorial of the index. We're getting 4 times 3 times 2, or 3 times 2. Right? Now, of course, the times 1 we're omitting, but you could always put that times 1 there. So what we've discovered here is generalizing this pattern. What we're seeing is that a sub n actually should be the nth derivative of the function. Notice there's a little bit of notation here. If you put this in parentheses up here, that represents the nth derivative as opposed to the nth power. So if you ever see parentheses in your exponent, that actually means you're talking about the derivative there. So the nth derivative evaluated at the center divided by n factorial. So we have our a sub n. We actually know what these a sub n's should look like based on the nth derivative of our function evaluated at the center divided by n factorial. Now, if you're not completely convinced by generalizing this pattern, what I would do is I would differentiate this one more time, get the fourth derivative of our function, which you can see is going to be just 4 times 3 times 2 times a sub 4, and then plus a bunch of other stuff that all have those x minus c's. Plug in the x equals c and determine a sub 4, and you'll see that it fits this pattern exactly. So we now know that these a sub n should be based on the different derivatives evaluated at the center divided by n factorial. All right, let's summarize this then. So this allows us to give the following definition. Suppose we have a function f of x. If this function has a power series representation centered at x equals c. So again, we're making that assumption. We don't know that all functions have these representations, but if they do, and they're centered at x equals c, then we call this representation the Taylor series centered at x equals c. And then the expression is f of x equals the sum n equals 0 to infinity, a sub n, x minus c to the n, where those a sub n's are equal to the nth derivative of our function evaluated at the center divided by n factorial. So in other words, if a function has a power series representation, we know what that power series representation should look like based on the successive derivatives of our function evaluated at the center. A quick note, if c equals 0, if we decide to center our Taylor series at x equals 0, so if the center is x equals 0, we often give these the very special name, the Maclaurin series. So a Maclaurin series is simply a Taylor series centered at x equals 0. All of the series that we have established so far, so the one we established for 1 over 1 minus x, ln 1 plus x, and arctan of x, those were all centered at x equals 0. So all of those ones we did in the last couple of videos, those were all examples of Maclaurin series. So everything we've sort of been doing so far has always been a Maclaurin series. We just didn't use that name. We just called it a power series centered at 0. But now that we've given this definition, in general, we call these things Taylor series, but when the center is 0, we just give them the special name Maclaurin series. So, what's the big deal about this definition? Well, this tells us that even if we can't cleverly manipulate a series we already know, so even if we can't figure out a way to substitute or multiply by a polynomial term or differentiate or integrate, we can still try to determine the power series representation of a function based on this explicit formula for what those sequence values should look like. So, to sort of help us see this, we're going to use this definition and we're going to build Maclaurin series for some other very sort of famous functions, namely things like the exponential e to the x and also the base trigonometric functions sine and cosine. So we'll get a chance to sort of practice this definition, but along the way, we'll come up with some other really important established series. So let's go ahead and do that. Let's determine a Maclaurin series for f of x equals e to the x, and then we'll have to determine its radius of convergence. Notice we're not going to just be able to state its radius of convergence, because we're going to be building this thing from the ground up. We're not going to be basing it on something we've already done where we can just use the previous radius of convergence. So we'll actually have to determine the radius of convergence, meaning something like a ratio or root test at the end. So let's figure out how we're going to determine a Maclaurin series for f of x equals e to the x. To do this, I highly recommend making a little table. So we're going to make a little table of n, which we'll do 0, 1, 2, 3, maybe 4. Then we'll also keep track of the nth derivative of our function. And of course, our actual function is e to the x, so we can put that in right here. Then we'll need to keep track of the nth derivative of our function evaluated at the center. Keep in mind here, since we want to do a Maclaurin series, evaluating at the center is going to be 0. Then we'll want to keep track of those constants, so those sequence size, the nth derivative evaluated at the center, divided by n factorial. And then our last column is going to be the actual terms of our series, meaning that it's going to have those sequence values and then x minus c to the n. Okay, now you can fill in this table however you like. You could go row by row, but what I would recommend doing is going column by column so you can do the same sort of operation. So if we want to fill in this, what we need to do is we need to take the derivative each time. So we got to take the derivative, then the derivative, then the derivative, then the derivative. Then we just plug in, then we divide by n factorial, then we make these terms. Okay, so let's fill this in by differentiating. So if we differentiate, we get e to the x, then e to the x, then e to the x, then e to the x. Now again, we're only doing the first couple terms just to establish a general pattern, and then we'll write out the full infinite series. So now we need to evaluate each of these at the center, which since it's a Maclaurin series, the center equals 0. So we'll just make a little note of that. C equals 0 here. So let's go ahead and actually evaluate those. At c equals 0, each of these is going to just be 1. Okay, then here we're going to have 1 over 0 factorial, 1 over 1 factorial, 1 over 2 factorial, 1 over 3 factorial, and 1 over 4 factorial. Now, of course, could I write out what those are? Sure, you can remember that 0 factorial is defined to be 1, 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, 4 factorial is 24, etc. But we don't really want to do that because remember, our goal is not to figure out these individual terms. We want to find a general pattern. So it's easier to write that general pattern with those n factorials there. So we might as well just leave them as the factorial. Now these terms, well, this will be our constant term, 1 over 0 factorial. Then 1 over 1 factorial. Since c is 0, we just have x. Then 1 over 2 factorial, x squared. 1 over 3 factorial, x cubed. 1 over 4 factorial, x to the 4th. So those are our individual terms. So we could say then that e to the x is equal to 1 over 0 factorial plus 1 over 1 factorial, x plus 1 over 2 factorial, x squared plus 1 over 3 factorial, x cubed, plus 1 over 4 factorial, x to the 4th, plus dot, dot, dot. So that's what e to the x looks like. Now, of course, this is sort of an ugly way to write this, so we want to try to come up with a representation as an actual infinite series. So we'll say this is the sum from n equals 0 to infinity. Notice that this fraction is always 1 over. If we think about this as n equals 0, this is n equals 1, this is n equals 2, this is n equals 3. The denominator is always based on the factorial, so we can put that as 1 over n factorial. And then this is x squared, x cubed, x to the 4th. We can think about that as x to the 0, so we can just put x to the n. So we have a power series representation for e to the x, a Maclaurin series for e to the x. E to the x is the sum from n equals 0 to infinity, 1 over n factorial, x to the n. That's how we were able to sort of describe the pattern that we were seeing here. Now we want to go ahead and determine the radius of convergence. So to determine ROC, well, remember, if you don't have the radius of convergence already sort of given to you based on a previously established series, we had two ways of determining the radius of convergence for a power series. We said that you could either use ratio or root test. Since there's a factorial in here, we probably want to just go ahead and use ratio. So we want to take a look at the limit as n goes to infinity. We'll plug in n plus 1, so we have 1 over n plus 1 factorial, x to the n plus 1, divided by 1 over n factorial, x to the n, all in absolute value. Let's go ahead and flip this up here and flip this down here and then take a look. So we have limit n goes to infinity, absolute value, n factorial, x to the n plus 1, over n plus 1 factorial, x to the n. Now we can do some simplifications. We know that we can go ahead and cancel this with this, and there'll just be an n plus 1 here, and we can cancel this with this, and they'll just be an x. So we should have the limit as n goes to infinity, absolute value x over n plus 1. Now we know that this absolute value really just applies to the x, so we can view this as the limit as n goes to infinity, 1 over n plus 1, absolute value x. And, of course, we can slide this absolute value x out there because the limit doesn't apply to that. We get absolute value x, limit n goes to infinity, 1 over n plus 1. Where is 1 over n plus 1 headed as n goes to infinity? Well, it's headed to 0, so we get absolute value x times 0. So remember, we're trying to determine the radius of convergence. So to converge under ratio test, you need this to be less than 1. So to converge, absolute value x times 0 needs to be less than 1. So this is always true. No matter what x you put in here, if you multiply it by 0, you're going to get something less than 1. So that tells us that our radius of convergence is positive infinity. So the actual power series we just established, this Maclaurin series up here, it actually is always a true relation. It's true for any x. So it's not restricted on a small interval. It's true for all x values. So we can say that e to the x, the exponential function, is the same as n equals 0 to infinity, 1 over n factorial, x to the n, for absolute value of x less than infinity. Or if you prefer, you could just say for all real numbers. But since we've always been writing it with that absolute value notation, might as well do it like that. So this is a huge step forward for us because so far we've only been able to sort of build series representations for rational functions, the logarithm, and the inverse tangent function. Now we've seen how to take something that's a really fundamental function, the exponential, and write it in terms of this infinite polynomial. Once again, we'll talk about, like when we get further on into 1111, we'll talk about how you could use this to come up with an approximation. Like if you wanted to know e squared, you could say that that's approximately going to be the sum n equals 0 to infinity 1 over n factorial 2 to the n. You do a few of those values, and then you could go ahead and come up with an approximation for e squared without using a calculator, just basic arithmetic. But for now, this is our sort of fourth major established series. We've got one for the basic rational, one for the basic logarithm, one for the basic inverse tangent, and now we have one for the basic exponential. All right, we also promised that we could do this for the sort of base trigonometric functions, sine and cosine. Let's go ahead and talk about those. So let's determine a Maclaurin series. So again, centered at 0 for f of x equals sine x, and then determine its radius of convergence. So we'll do our same sort of approach. We'll make a little table, 0, 1, 2, 3, 4. We'll keep track of the derivative. We'll keep track of the derivative evaluated at the center. We'll keep track of those sequence terms, so the derivative evaluated at the center over n factorial. And then we'll keep track of the actual terms, the derivative evaluated at the center over n factorial, x minus the center to the n. Okay, and again, we're going to make a little note here. C is going to be 0 for this. Of course, later on, second half of 1110, we'll see some examples of building things that are not centered at 0. So that's why I'm sort of writing this out in general. But right now, C equals 0, so it's going to be pretty easy to do this. And of course, the first part that we can fill in with this is that our original function here is sine x. Certainly, you could go ahead and fill all this stuff out, but it's easier to probably take care of all the derivatives. Derivative of that sine x is going to be cosine x. Derivative of that cosine x is going to be negative sine x. Derivative of that is going to be negative cosine x. Derivative of that is going to be back to sine x, and so on. Of course, if we can't figure out the pattern after we do these, we could always add more to our table. We're just trying to do a few to start off with. Now we're going to evaluate each of these things at 0. So it looks like we should get 0, and then 1, and then 0, and then negative 1, and then 0. Here, well, if we have a 0, it's just going to be 0. So it looks like we're going to get 0, 1 over 1 factorial, 0, minus 1 over 3 factorial, 0. Here we're going to have 0, then 1 over 1 factorial, x, 0, 1 minus 1 over 3 factorial, x cubed, because we're on n equals 3, and then 0. Okay, so this is sort of special. There's several things that we should sort of make note of here. Well, first thing we should probably notice is that we are only getting the odd terms. The even ones are always zeroing out here. So we're only going to have the odd terms. So odd terms only. How do we represent odd numbers? Well, if we plan on starting from n equals 0, then the easiest way to sort of represent an odd number is 2n plus 1. So notice that we're only getting sort of the odd factorial and the odd exponent. So that means we want to use 2n plus 1 for those factorials and for those exponents. We can also see that we got positive, negative. If we did another one, we'd be back to positive. So we also have alternating terms. Okay, alternating terms we often represent with a minus 1 to the n. Notice that since it does start positive and we plan on starting at n equals 0, we will, so alternating terms starts with positive, so we will use minus 1 to the n. So we're going to need that 2n plus 1 to handle the factorials and the exponents, and this minus 1 to the n will need to sit in front to make sure that it alternates. So what can we say here then? Well, we can say sine x is equal to the sum from n equals 0 to infinity. We said we want to make sure we have those alternating components, so minus 1 to the n. Then numerator is always just 1, right? Up here is always just a 1. Then denominator is based on those factorials, but we're only getting the odd factorial, so 2n plus 1 factorial. And then x to the different exponents, again, only odd exponents, so x to the 2n plus 1. So we have minus 1 to the n, that guarantees that it alternates, which we know it needs to do. We have 2n plus 1 factorial because we only are getting the odd factorials, and we have x to the 2n plus 1 because we're only getting the odd exponents. Could you write this a different way? Well, you actually could. If you wanted to start your series from n equals 1, you could do it as minus 1 to the n minus 1, that would still be positive. 1 over 2n minus 1 factorial, that's another way of phrasing odds, and x to the 2n minus 1. This is sometimes called re-indexing. But in general, we've started all of our series in this class at n equals 0, so that's what I generally try to do when I'm trying to build these representations. Okay, so we now have a Maclaurin series for sine of x. Can we figure out its radius of convergence? Well, again, we built it sort of from scratch here, so we're going to need to use something like ratio test. So to determine ROC, we'll use ratio test again. Why are we choosing ratio test again? Well, it does have that factorial in there, so we might as well go ahead and use it. So we'll need to take the limit as n goes to infinity, absolute value, plug in n plus 1 in here, so I guess we'll have minus 1 to the n plus 1, 1 over 2 times n plus 1 factorial, x to the 2 n plus 1 plus 1, all divided by minus 1 to the n, 1 over 2n plus 1 factorial, x to the 2n plus 1. Okay, a lot of messy stuff here. What I'll first do is I'll sort of apply the absolute value just to this stuff because this is just going to be negatives or positives. The absolute value is just going to get rid of those anyway. So we can view this as the limit as n goes to infinity. Let's flip this up and flip this down and also simplify our exponents. So we have absolute value, 2n plus 1 factorial, x 2 times n plus 1 is going to be 2n plus 2, plus another one, 2n plus 3. So x to the 2n plus 3 divided by 2n plus 3 factorial. Again, same simplification down here. 2 times n plus 1 is 2n plus 2, plus another one, 2n plus 3. And then we have x to the 2n plus 1. Okay. All right, let's go ahead and simplify these. This and this are going to cancel, and we're just going to get x squared. For this and this, probably good to remember that 2n plus 3 factorial is 2n plus 3, then times 2n plus 2, then times 2n plus 1, then times 2n times ... But all of this stuff is going to be 2n plus 1 factorial. So if we cancel that, we're just going to be left with those first two terms. So this will be the limit as n goes to infinity. Up top we'll have x squared, and in the bottom we'll have 2n plus 3 and 2n plus 2. Notice it makes sense because normally when we cancel n factorial n plus 1, we have one term. Since this has that 2n, every time we move forward 1 in n, our factorial gets 2 additional terms. So when we cancel here and here, we're left with 2 things in the denominator. Okay, now we know that this absolute value really just applies to the x squared. So we can view this as the limit n goes to infinity, 1 over 2n plus 3, 2n plus 2, absolute value x squared. And of course, then we know that this doesn't have anything to do with the limit, so we can stick it in front, which is absolute value x squared, limit n goes to infinity, 1 over 2n plus 3, 2n plus 2. Where does this limit head? Well, we don't even need to multiply this out. This is going to infinity, this is going to infinity. They're being multiplied. It's still going to go to infinity. This is going to approach absolute value x squared times 0. So to converge, we need absolute value x squared times 0 to be less than 1, which is always true. So we get that our radius of convergence is positive infinity, once again. Notice back way from our discussion about speeds of expressions, we could have guessed that e to the x and this sine x would both have radius of convergence positive infinity, because if we look back at the expressions we're getting, remember, whenever you choose an x value, this is going to be exponential in nature, but the factorial, we said, is a whole level faster than the exponential. So once you choose an x value, this will be exponential, this will be factorial, which is going to be way, way faster. This is always going to win out, and the thing's going to converge. So, of course, the e to the x and sine x both had the sort of infinite radius of convergence because they both involve this factorial in the denominator. For now, though, since we know that the radius of convergence is positive infinity, we can summarize that sine of x is equivalent to the sum from n equals 0 to infinity, minus 1 to the n, 1 over 2n plus 1 factorial, x to the 2n plus 1. And that holds for all x, or we could say for absolute value of x less than infinity. Okay, so now we've gone ahead and we've built 2 Maclaurin series from scratch, just by using the sort of definition that we determined for those sequence values based on the nth derivative of the function evaluated at the center divided by n factorial. So if we ever need to sort of build a series from scratch without using a previous established one, this is the approach we're going to be using, where we make a table, look at what the terms ultimately look like, try to diagnose how to represent those as a pattern, things like odd terms only or alternating or things like that, and then write out that actual general series. We'll get to do more examples of that, especially in the next sort of part of 1110, where we start to build some Taylor series that are not centered at x equals 0, and then we'll make use of this table approach more. So we'll still see some examples of this. For now, though, we got a series representation for sine of x. Let's go ahead and build one for cosine of x. So we want to determine a Maclaurin series for f of x equals cosine x, and then state its radius of convergence. So if we wanted to, we could do exactly what we just did on the previous page and build a little table with the n and get some of those and do the same thing. Wouldn't be too bad to do. But keep in mind, you still have all your manipulations. You still have substitution, you still have multiplication by a polynomial term, and most importantly, you still have differentiation and integration. And we know sine and cosine are very intimately related between their derivative and integral. So let's go ahead and grab the previous, what we just did. So we'll grab this stuff here and see if we can just use this to very quickly determine one for cosine. So we'll go ahead and just pop this here. So remember, we've got this. So how could we get a cosine? Well, we know the derivative of sine is cosine, so let's differentiate both sides. So we take the derivative of sine, and we differentiate here. 1 over 2n plus 1 factorial x to the 2n plus 1. And we're going to differentiate all of that. Remember, differentiating and integrating do not change radius of convergence, so this will continue to be absolute value x less than infinity. Notice I sort of put that subtly into the wording here. It said state its radius of convergence. We won't need to determine the radius of convergence. Because, well, we can just use the previous one and our knowledge that the derivative doesn't impact that. Okay, over here, the derivative is going to be cosine x. Over here, we know that the derivative is going to apply past this and just impact this x to the 2n plus 1. So we're going to get the sum. Remember, we got to be a little bit careful about where it starts from. So I'm just going to say the sum to infinity for right now. Minus 1 to the n. This exponent is going to drop down in front. So we get 2n plus 1 over 2n plus 1 factorial. And let's subtract 1 from the exponent here. We get x to the 2n. Now we got to ask ourselves, do we really lose that first term? Does it make sense to still have n equals 0? Well, n equals 0 in here is x to the 0, which is a constant. That's fine. So we would still have n equals 0. So we don't lose the first term like we did in the sort of previous video where we took a derivative and we lost that n equals 0 term. Another way to think about it is that in this expression, when n equals 0, this right here is actually x to the 1, which when you differentiate it does stick around. It becomes a constant, but it's still there. It doesn't just get annihilated and become 0. So in this case, it's still going to run from n equals 0 to infinity. All right, this of course still has the same radius of convergence, absolute value x less than infinity. Okay, anything we can do to simplify this? Well, let's think about this 2n plus 1 over 2n plus 1 factorial. Keep in mind 2n plus 1 factorial is equal to 2n plus 1 times 2n minus 1 times dot dot dot. So if we cancel that with that, we'll have all of this stuff, which is 2n factorial. So we can get that cosine x is the sum from n equals 0 to infinity. Minus 1 to the n, we cancel that out, 1 over 2n factorial x to the 2n. Absolute value x less than infinity. So without having to do all that sort of messy work with the table, we were then able to build a Maclaurin series for cosine x just based on the one that we built for sine. Okay. At this point, we've done several examples of building these Maclaurin series. We should tie this together with what we've already done from 11.9, where we built some other power series representations. Let's summarize all the really important established series that we've already done the work for. So this you can consider as sort of our summary of Maclaurin series. And actually, these are going to be all the Maclaurin series that we use as established series. We're going to build some other ones, but these are the ones that if you ever see something that says use any established series, you want to reference back to. So we have 6 established series overall. These 3 we established back in 11.9 by using the geometric series formula and then other manipulations. And these 3 are the ones we just did using the sort of more manual Taylor series, Maclaurin series approach. These 3, right? Here's one for the rational function, for the logarithmic, and for the inverse tangent function. Each of these all have radius of convergence equal to 1. So these have a limited radius. These 3 all have an infinite radius of convergence, and that's all because they all involve that factorial in the denominator. A couple interesting things, the arctangent and the sine of x each only include the odd powers of x. That is because both arctangent and sine are odd functions. Remember, arctangent looks like this. This piece, if you reflect it over here, is equivalent to this, so it is an odd function. Sine looks like this. Same thing, you take these pieces, you reflect it here and then down, you get these pieces. So both arctangent and sine are odd functions from algebra. That's why they have only odd powers in their polynomial expansion. For cosine, same idea, except that it's got only evens. If you think about the graph of cosine, what's on this right-hand side exactly matches what's here, right? It's symmetric across this, so it is an even function. That's why you have only even exponents there. So definitely make sure you commit these 6 established series either to your memory or write them down in your notes. They're very important. Anytime you see a question that says use an established series to build another series, you want to base it off of one of these 6. Also keep in mind, not only do we have these series formulas, but we also have the radius of convergence for each of these. Last thing to comment is remember that the manipulations that we have substitution. Substituting into one of these three can change that radius of convergence. Substituting into these will never change the radius of convergence because it doesn't matter what you substitute. If the radius starts infinite, it'll remain infinite. So you only really have to worry about the radius of convergence changing when you substitute into one of these three where you have a finite radius. You also have multiplication by a polynomial term with the same center. Since all of these have center 0, they're all Maclaurin series, you could only multiply these by other polynomials with a center at 0. So things like a constant times x to an integer exponent. And then finally, remember, you also have differentiation and integration. Now, unfortunately, differentiating or integrating most of these aren't going to lead many places because we built these off of integration and differentiation. You differentiate this, you're just going to get this guy. You integrate this, you're just going to get back to this. So that's probably not going to be used too commonly, except maybe on the rational one, because we've already sort of exhausted the usefulness of those differentials and integrals. All right, let's wrap this up now with just trying a couple more examples using some of these new established series to just take a look and build some other ones based on those manipulations. So let's use any established series to determine a Maclaurin series for f of x equals 4x cubed sine of 2x cubed and state its radius of convergence. Notice you could try to do this with that sort of table approach, but the derivatives of this are going to get really messy. You're going to have to use product rule and chain rule, all that stuff. You don't want to have to actually do it the sort of brute force way. You want to use the established series. So let's start by looking at this component here. Obviously, this is just multiplication by a polynomial, so we can deal with that at the end. So we can say sine 2x cubed is equal to, well, if we let z equal 2x cubed, then we could get this to be sine of z. We just built an established series for sine, so we could say this is the sum from n equals 0 to infinity, minus 1 to the n, 1 over 2n plus 1 factorial, x to the 2n plus 1. And of course that holds for all, that should be a z to the 2n plus 1 because we're using our new variable z, and that holds as long as the absolute value of z is less than infinity, so for all z. Okay, let's go ahead and pop this back in there. So we get the sum from n equals 0 to infinity, minus 1 to the n, 1 over 2n plus 1 factorial. Instead of z, we're going to have 2x cubed, parentheses to the 2n plus 1, as long as 2x cubed in absolute value is less than infinity. Okay, should be pretty easy here. We can distribute this onto both. This is going to give us a 2 to the 2n plus 1, and then power to a power we're going to multiply. So it looks like we should have the sum from n equals 0 to infinity, minus 1 to the n, 1 over 2n plus 1 factorial, 2 to the 2n plus 1, x, 3 times 2n plus 1 is going to give us 6n plus 3. And then, of course, this, you can divide by 2 and cube root, not going to change anything as long as x is less than infinity. If you want, last thing I might do is just put this here so that all the constants are here and the sort of power terms are there. So we can summarize that sine of 2x cubed is equivalent to the infinite polynomial, the sum from n equals 0 to infinity, minus 1 to the n, 2 to the 2n plus 1, over 2n plus 1 factorial, x to the 6n plus 3, as long as the absolute value of x is less than infinity. Okay, there's a Maclaurin series for sine of 2x cubed. We wanted 4x cubed sine of 2x cubed. So let's multiply both sides by 4x cubed. So 4x cubed sine 2x cubed is just going to be 4x cubed sum n equals 0 to infinity, minus 1 to the n, 2 to the 2n plus 1, 2n plus 1 factorial, x to the 6n plus 3, absolute value x less than infinity. Remember, multiplying by a polynomial term with the same center has no impact on the radius of convergence, so we're all good. This we know distributes right in. This x cubed is going to add to there. So we get that 4x cubed sine of 2x cubed is going to be the sum from n equals 0 to infinity, minus 1 to the n, 4 times 2 to the 2n plus 1 over 2n plus 1 factorial. Add the 3 in there, x to the 6n plus 6, as long as absolute value of x is less than infinity. This gives us a power series representation for a very sort of messy expression here. This polynomial mixed with this sign in a composition. But notice we were able to get this representation very easily by using the established Maclaurin series and our standard manipulations of substitution and multiplication by a polynomial term. One thing I do want to notice is if you wanted to clean this up, again, I would totally accept this. I think this is fine. But if you wanted to, you could be very clever and call 4 2 squared, put that in here, and I suppose you could come up with a slightly nicer one. 4x cubed sine 2x cubed is the sum from n equals 0 to infinity, minus 1 to the n, 2 to the 2n plus 3, because that 4 is 2 squared, 2n plus 1 factorial, x to the 6n plus 6. Absolute value x less than infinity. And again, even though this would be totally sufficient, if you want to just remember what this really means, what we're saying is that 4x cubed sine of 2x cubed is roughly, if we wrote out the first few, we'd get something like when we do n equals 0, it would be positive, so you get like 2 cubed over 1 factorial x to the 6, and then minus 2 to the 5th over 3 factorial x to the 12th, so on and so forth, right? So you're getting sort of that crazy polynomial represents this thing actually everywhere. Okay, let's wrap this up with one more example and actually answer a question that we talked about ages and ages ago that we said in its current form is sort of unanswerable. But now that we have this power series, this Maclaurin series approach, we actually can come up with an answer for it. So we're going to use an established series to determine an antiderivative of e to the x squared dx. And remember back when we were talking about techniques of integration all the way back in chapter 7, we said there are some things out there that don't have closed form antiderivatives. And e to the x squared is an example of that. There is no closed function expression that is an antiderivative of e to the x squared. But we can do this using our Taylor series and Maclaurin series approach. So we're going to go ahead and figure out how to take an antiderivative of a function that we didn't know how to do. And we'll have to do that through this Maclaurin series approach. So we're going to start with e to the x. Well, we can go ahead and actually start with our e to the x squared. And we'll call that e to the z. Let z equal x squared. Then, of course, we can use the established series we have for the exponential. So this will be the sum from n equals 0 to infinity, 1 over n factorial, z to the n, as long as absolute value of z is less than n. Then, notice that we can say that that is the sum from n equals 0 to infinity, 1 over n factorial. Let's pop this x squared back in there. So x squared to the n, absolute value x squared. Oh, this should be an infinity there. My apologies. Less than infinity. Okay, then we can go ahead and simplify this. Looks like we get that this is the sum from n equals 0 to infinity, 1 over n factorial, x to the 2n, and this we can go ahead and simplify and get absolute value of x less than infinity. Okay, so what we've just done is we built a power series expansion for e to the x squared equal to this. So we now know that e to the x squared is equivalent to the sum from n equals 0 to infinity, 1 over n factorial, x to the 2n for all x, or x less than infinity in absolute value. Okay, now let's go ahead and integrate this. So we'll integrate e to the x squared dx and integrate the sum from n equals 0 to infinity, 1 over n factorial, x to the 2n. Absolute value of x, of course, is still less than infinity, and this is dx there. Okay, we know that this integral distributes over the infinite sum, so we can say that the integral e to the x squared dx is equal to the sum n equals 0 to infinity, 1 over n factorial. Integrate this, add 1 to the exponent, so x to the 2n plus 1, divided by that new exponent, 2n plus 1. Put all that in parentheses, add your constant, And there we go. It might not be the nicest, cleanest form, but we now know we have an antiderivative of e to the x squared dx. I mean, e to the x squared dx, or e to the x squared, is a continuous function. So it has to have, the integral makes sense, it's integrable, but we've never had an actual way of integrating it. And now we do. We have to integrate it as a Maclaurin series, and the answer, quote unquote, is a Maclaurin series, but there we go. We have now an antiderivative of e to the x squared. You could even use this as an alternate way to approximating it. If you remember back either in one of the videos or in some of the suggested exercises, we used approximate integration to determine like the integral from 0 to 1 of this, because again, we couldn't integrate it, so we used something like trapezoidal rule or midpoint rule. Well, now if you wanted to do 0 to 1, you could also do it this way. You could plug in 1 to this, you could plug in 0 to this, take the difference, and that would give you another way of sort of understanding or estimating the definite integral. So this is sort of an advantage of this power series representation. Again, power series are infinite polynomials, and polynomials are really easy to do calculus with. Taking their derivative, taking their integral, very simple. So even though this thing it doesn't have a closed form antiderivative, we now at least have some form of an antiderivative for it. In our next video, we'll finish up 11.10 by doing a couple examples of building Taylor series that are not centered at 0. So we'll build them at other sort of centers, and we'll investigate a little bit further what types of functions actually have these Taylor series representations. Remember, everything we did in this video worked under the assumption that a representation existed. We said if the representation existed, this is what it should look like. In the next video, we'll talk a little bit about how we know that representation actually exists.